Hey, what's going on? This is Scott Perry back with another Touchdesigner tutorial. In this video, we are going to walk through how to apply pops to build out an LED DMX profile using LED strips. In my day-to-day, we are using a LED infinity mirror dance floor. It's comprised of 96 tiles, each tile featuring 28 lights in one square, and the signal pumps in one side of the dance floor and then snakes around the other end. So with the LED DC power, we can pump power in from both sides and signal in from one. So all of our cables are coming off of one side of the dance floor. Why does that matter? Touchdesigner has made some cool new features that kind of simplify splitting up universes and sending out from transmitters like the LED DMX Max 4 that I'm using. I guess it's called the LEDMX Max 4 from DMXking.com. I know it's widely used over lots of places. With the DMXout profile here, they're offering better transmission. I don't have it plugged in right now, so it's not highlighting, but on the serial here, this says DMX King port. It's set up just for the applications that we're already using. And instead of having to port it back over to the CPU, we get all of our computations on the GPU and getting a little bit more power in the engine. So everybody's happy. In this example, we're going to derive the color from the position of our particles or points. I kind of use those terms interchangeably, forgive me. In this case, we are talking about points on a pop. We can add a little bit of noise to the colors to give it a little bit of dynamic generation. And what we can also just call it directly from top here in our network. So we can change the phase of this one and see that they're indeed changing. So if you take a look at this network, it's actually pretty straightforward, only about 25 operators, and there's no like real magic. So we'll start from the top and work our way to sending out signal out of DMXout POP. So strap in. Hope you're ready for some syntax and stuff because it gets fun and the possibilities are endless, as they say. Free thinking environment for you. Here we go. All right, starting from scratch. Nothing at all in the network. Let's drop down our rectangle. That's what our starting building block is going to be. We've got our, each tile is going to kind of go in a square, and then the next one will be oriented the same way. And then every other row will rotate 180 degrees. So it gets a little funky with the way that they pivot and that sort of thing. So we'll just start from the top, and you can here just a little bit of housekeeping. Let's put a null at the very end, as we often do, and we'll just say floor out. And there's a great little tool in the palette called the Pop Viewer, and that's what we're going to use. We have a panel view on this side, and we want to call our Pop Viewer there. So now if we put the floor out onto our object, you'll see our rectangle. However, we want to connect this as line strips. And we have now, you'll see 4 points. So let's do a line divide. And we want to divide this 7 times per point because we have 28 pixels. Now we have 28 points, and I'm going to drop a primitive down to delete the primitives and keep the points. So now we have 28 points in our pop viewer. Let's go, and if you see here on the left hand side, we have a P next to a green circle. That is a different indicator that you can toggle on. So we can toggle on all these different values here to kind of use different forms of maybe an arrow to represent a direction, or you want a dot to represent a color. This color is here indicated from 0 to 1 on X and Y. And it is currently normalized. If you click on this yellow dot here, you can see this dot color auto range will change the way that the colors are represented here. We can also increase our dot size, and that might be helpful for people who are watching at home. So we'll just turn that up a little bit. I have a feeling we're going to turn that down again in a minute, but for now, it's pretty cool. So there we have our primitives, and since we're going to be kind of using these in a 0 to 1 scale, let's move this a little higher up. So that can happen with a transform. And there's a cool new tab on these transforms called Align. We'll use that a little bit later, but for now we know that it's 0.5 to 0.5. So, oops, 0.5 to 0.5. Okay, so what's that? 0.5. Now I'm going to hit H on my pop viewer to bring me back to home. I like to use X and Y coordinates, even though technically this dance floor goes X to Z, because when you hit the H, it homes on the vertical axis. So if you do it in X and Z, every time you hit H, it just makes a line of flat points. So we'll work in Y. There is the first square. We can also perhaps look at our point numbers on here, and you can see that we have, starting in the top left, 0 all the way to 27. Actually, the way that my dance floor works is the point that is currently numbered 15 is the 0th point on the LED strip. So I would like to do a sort pop here, and this has a cool shift value where I can move this around to be the number that I want. And I think I want 15, 13. And that gives me the orientation that is realistic to my dance floor. Now, as I highlight over this, you'll see that it says 28 out of 29 points. That is indicating how many points you're actually doing work on and how many points the computer has saved in memory. I prefer to use like 28 out of 28 points instead of what's currently happening. It's just a little faster on our computer. The GPU can handle millions of these points. So at most, for this dance floor, we're going to have 2,688 points. And I'm not too worried about the overhead we're losing on this particular example. If I were going to use this long term in my use case, I would create a point operator that looks like this. So this is just the same exact thing, except instead of 28 out of 29 points, it's just 28. All I really did was create these points and then pump in the values I knew were correct for their location. You can do this if you want. Not necessary, I think, for today's use case. So we'll just keep it moving with the way it currently exists. Cool. So now that we have this single tile, we need to use a copy pop to move these around. You can use a grid as the basis for your copy pop, and then use some GLSL to rotate the squares on every other row. I think it's a little easier to explain if it's explicit in these pops. So let's start with a line pop. And it's going to, on your points tab, go from 0 to 11. And the name of the game here are attributes. Attributes can be used on these points to rotate them or color them or scale the size. But for this example, we are going to use the built-in rotation attribute that the copy pop is looking for. Here on the template page, there's rotation and pivot. And our rotation is looking for a vec3. And we're just going to start with a standard 0, 0, 0. And then I'm also going to transform this by 1. Move it down. Oops, I don't want to do it on the Z. I want it on the Y. And I also want to rotate it 180 degrees. But we want the pivot there to be at 6, 5.5. That's half of 11. So now we have 2 lines of points, and the first line indexes upward from left to right, and the second line is down 1 unit and indexes from right to left. And here we are going to do a math mix to change what the rotation is. So we just want this to read 180, and we want our rotation Z value to be 180. We're going to back it up just a notch here and go back to our attribute. We want our rotation to happen in the middle of the square, which happens to be 0.5. So let's add one more pivot attribute, and that is also going to be a vector3, and we are going to read 0.5.50. So now we're going to put in one more line here, because now that we have 2 of our rows, we need 4 rows total. So this point is going to start at 7 and end at 1, I believe. Might end at 2. We'll see in a moment. So if we do the copy pop again, well, we'll pop this one in here. And you can see we have too many divisions here. So the divisions on our vertical line needs to be set to 3. So we want 4 points total. Oh, and we need a merge here. A merge to construct both of our lines. And now looks a little goofy. It should be evenly spaced. So I must have my vertical line here incorrect. Points 71. And that looks pretty good. So now we have our let's do a little bit of housekeeping here, and I'm gonna move all this a little to the left. We'll keep our floor out over here, put another null in here and call this square. Now let's do one more copy. this to this. All right. Something's goofy. All right, I have the wrong number of divisions here. This should not be 20. This should be 11. Now we have 12 points here. And our square is looking correct. So I'll pump this back to our pop viewer here. Hit H for home. And you can see, again, we have our point size scale too high. And now when we zoom in, we can see that we're going from 0 to 12 on our size and 0 to 8. But one of the unfortunate things that's happening right now is our points are showing up in the exact same place for our square. So we might go right before this square null and add a transform. And we'll have our pivot be 0.5, 0.5 again. Oops, too many decimals. And let's scale this by 0.875. And now we have all of our points equidistant on our square. You can see that we've moved our points inside the X and Y axis here by a margin, and they're all sitting in there nicely. I would turn off the dot auto range, and you can see that our values are going all the way to 11.94 essentially, and close to 0. If you highlight over here, you can see that's 0.0625 for our X value on this end. And over here, we have 11.94. One more change that we want to make here as we scroll into the numbers of our points here, I'm going to turn off the color just so we can see the exact point numbers. We're going to go all the way to the top and see here. We need to rotate these points, well, all of these squares, because the signal routes down one way and around the other. So we have already accounted for that in our attributes that we've created. But what we need to do is click our rotate and pivot and activate them. So now you can see here our 336th point. If I turn this off, it's just rotating each square 180 degrees. Cool. So this is the setup for how my LED floor would work. And now what we want to do is create a UV value so we can basically apply a texture to these coordinates. So let's use a math mix to edit our texture attribute. If we middle mouse click here, we can see that there are currently 3 attributes: point, normal, and texture. We're gonna take texture and reconfigure it to equal our points from left to right. Currently, they are setting up our points in each individual square goes 0 to 1. So let's put a lookup texture in here, and we'll put our math mix in, and just to see it in action, we'll create a ramp top and put a null after it. And now equate our resolution to what we are currently working with, and just make a little ramp, put it in here in the lookup texture for our top, and we want to output to color. And now if I change the P to color, you can see that the UV, the texture is set up to go in the square, as I had mentioned. So now let's take this math mix and say we want A divided by B, P0 divided by 12 equals text 0. And then we'll add the same thing for P1 divided by 8 equals text 1. And, oh, actually, we don't want to be using P0. In any case, we want to be using texture. Oops, screwed that up in the explanation. Okay, so here it is working as we would want with UV. If I bypass this mass mix, you can now see it actually is going in a square for what was initially set up with the rectangle from 0 to 27 for the point numbers. We change this to go from left to right. If I change this now to text, you can see our UV map, and back to color. As we switch the phase here, you can see it all rotates through, working, behaving like we would want. Cool. So that is the simplest way to like apply any texture to your fixtures as they lay in 2D space. You can even do 3D here with like a cache situation on our lookup texture. You could use your attribute W. For our purposes here, we'll just apply video to our dance floor. Next, we will derive our colors from the position in GLSL. So let's drop down this GLSL pop and look at the syntax that we have here. You have, as I uncomment this out, P is our attribute that we are sending out. When I click off here, it's going to give us an error because you have to be explicit on what attributes you are writing out of this GLSL. Anything that you want to affect and change needs to be called here in this output attributes parameter. We'll be working with color right now, and now it's saying there's a mismatch again. So let's add color in here, but now it's saying it's not a vec4, so we'll say RGB for the P. Okay, so now we have seen this before. This is the P value colored. So let's affect the hue with the Y position of all of these lights. So we'll assign start hue as 0, red. As we affect the hue by decimals, it will shift through the degrees of visible color to the human eye. So let's say start hue plus equals the floor of the TD in P dot X divided by 8. We'll do Y. Y divided by 8. Okay, that's not really going to call anything quite yet. So let's call a vector 3 hue color equals TDHSV to RGB. Oops, this T needs to be capitalized. And then we'll call start hue 1 point. And then we'll call hue color here. Oops, and we have an error. No matching overload function found. Oops. TDHSV to RGB. Pause this for a second, check my notes. All right, got it, fixed it. This needs to be a vec3. inside of this function, and we are indeed capitalized from the start. Okay, perfect. So now we have our y value changing it. Let's include the x value. Cool. And now we have all of our squares independently colored, so you can see the math working. So far we have colored our points using their position. To reiterate, we could say hue color equals TD in P. And now we have colored our points with the actual XY position and Z, but Z is 0 all along here. So comment that out. We have also earlier colored our points using the UV space that we have generated and applied a texture like this. And now in this latest step, we have used their position to generate a function and achieve the colors we were hoping to use. The great thing about this, these points are not in order, you know, but they are using their points to alleviate some of the computations we would have to do to find out where in 3D space or 2D space these points live. Now, let's synthesize our own attribute and use that to further edit the points that and colors that we have just created in this last GLSL script. So let's, before this GLSL, actually, let's just make this a completely separate. We'll keep going after the function. We'll add a new attribute. So here, we're going to put a noise pop down. And immediately you can see that it is affecting the output, but of the position attribute. But we actually want to say combine operation none. We just want the straight noise attribute, and it has created a new vector3 float noise attribute. So each point has its own noise. Let's change our color to noise on our, let's see, turn this amplitude up. So again, I'm going to click on the yellow dot here on our pop viewer and turn on our auto range again. And now you can see our colors. If I switch this to just the red value of our noise, you can see how the noise is applied to each of the points. Now I'm going to translate this with a little bit of time. And we have a little bit of motion. So now we have a noise attribute. We can call it as a float or vec2 or vec3. And we want to affect our color. So I'm going to put down another GLSL. And we could have done this in the same GLSL, but for a little clarity, we'll keep the scripts separate right now. Turn this to color. And if you remember, we need to declare color as an output attribute. And we're going to take the input color. Actually, you know what? I am going to do this all in the same script just to save this HSV adjust movement here. Let's do this. We'll delete this GLSL, reroute this noise to be before our initial GLSL script, and going back into this compute, above where we assign our hue color, we will say start hue plus equals TD in noise dot R. Now, if we go back to our color, you can see that we are affecting the color with the noise. We'll go back to our amplitude on our noise and scale this back quite a bit. So if it's 0, it's every grid changing as we have seen it, and now as we turn up our amplitude, each of the pixels changes. Very cool. If you don't change this to a float here, it'll throw an error saying that the vec3s do not align, cannot convert from a vec3 to a float. If you wanted to, you could choose to do any of the other ones. All right, cool. Now, I want to show you one more trick here, and that is to keep the points as we're utilizing them here in our main stream, and then reroute some of them. So we are going to create a new function based on an adjusted position attribute for all of our points, and then combine the attributes back into the original flow. So we can use a distance function or a length function. So I'll do everything after what we've been using so far. But here we're going to use another transform in a separate stream. And I want to use the align tab to move the points to the origin. And now using a math mix, I want to use a length function of the P attribute. And I want to call this distance. And let's drop down an analyze pop here. And I want to use the maximum of our distance and see what we're working with. So if I now put a pop2 dat here, I can see the max distance is 7.12. So in this max distance, or I'm sorry, in this math mix, I'll do A divided by B. And I just want to get the unit value of the distance. So we'll say dist divided by 7.12. Make it 7.125 just so that we get all of our maximum distances a little bit below 1. And now we'll do an attribute combine. And if we say that we want to pull in distance here, now if I change my color to distance, we get a unit circle from 0 to 1 value. And we could put in a function, the GLSL, to say I want to affect my color. Okay, so here so far we have nothing. Oh yeah, TD in dist. Now we've got our distance from the center of the dance floor being essentially the alpha multiplier of all of our color. If we move this around a little more, I'm gonna drop another transform after this transform that sent us to the origin. And as I move around the pixels or the points, as we move around our points in 3D space, our alpha is affecting all of our color, even though those points are not ever moving. They are all staying in the same place. Okay, there's one last thing that I want to talk about, and that is what it takes to actually pump these pixels out of a DMXout node. I'm gonna bypass this alpha adjustment here. But the first thing that I want to do is drop down a DMX Fixture POP. And this DMX Fixture POP does some pretty cool things. The first thing that we want to do is the first channel block is always minimized down here. So let's open that up by clicking these two arrows on the right hand side of our name. And in our situation, we want to pull out RGB. And I'm going to, for our sake, name it CD here as our DMX channel going out. And then I want to call our attributes color 0, color 1, color 2. And that's going to give us our RGB bytes, I guess you would call it. And if you put color 3 in here, or if you just put the whole color, then you would wind up getting the alpha values, which for our strips we don't want to use. The cool thing about this DMX fixture POP is that it will quantize the universe by our components or by our fixture. We want to use components because we don't want the B pixel to be split from the R and the G values. In our case, 512, the number of channels on a DMX universe, is not divisible by 3. So we want to stop at 510 channels per universe and then carry over the R and the G from the next pixel into the first pixel of the next universe. This quantized universe by components does that automatically. So it will make sure to never split our color 2 from our color 1 and our color 0, which is nice because we are sending 4 universes in every stream of signal coming off of our DMX King piece of hardware. There's one more thing that we need to do. Well, two more things that we need to do. We need to put down another primitive pop at the end here, and we want to connect our we want to create a line strip of points by pattern. No, let's see, by set. And the set, we want to group of n points. And in our case, we have 672 pixels included in each of the two rows. So we'll put 672 on our primitive. And if you look close now, we have lines created to link up here at the end to go from our last point of our 12th tile to our first point of our 13th tile going the other direction. Now, what we've done here with this primitive pop is declare each of our blocks of 2 rows is one fixture. So in our case, we now have 4 fixtures of 24 tiles. And that is the way that our DMX fixture pop here knows what universes it's going to send on. We will split up each of these fixtures. One more piece of information that the DMX fixture pop needs to know is, in our case, 24 blocks of 24 tiles do not actually fully fill out 4 universes. There are still 24 empty channels at the end of our 4th universe by the time it gets all the way around. So we need to put 24 into our channel gap here, and that will align our second fixture at the beginning of the 5th universe. So once you have that finished, I actually went ahead here moments ago and added a DMXout POP. The DMXout POP documentation is pretty good on the wiki for Touch. If you need a little more information, there's even better documents on the DMXout CHOP, and especially the networking information. That's all kind of interchangeable. One thing that I've learned along the way is if you use 255.255.255.255 in your network address, it kind of sends out to all listening devices out there and kind of keeps things steady when it comes to switching IP addresses on laptops or networks or something like that. So something to consider. And this is just kind of like a get out of jail free card if you use 255 4 times in your network address. Anyway, that's an easy thing to figure out. Once you sort it, it's sorted. I'm sure if you made it this far in this tutorial, you'll have no problem getting out of a DMXout operator. Appreciate you checking in and tuning in. I think this is where I'm going to wrap it up for today. Let me know if you have any questions or if I did anything crazy wrong. Hopefully this doesn't change too much where this becomes obsolete information, but in any case, I know the folks at Derivative have our best interest in mind. I can't wait to see where we go from here. Thanks a lot. See you soon. Bye.